Welcome back to Inorganic Chemistry. In the second part of Chapter 7, we'll continue looking at solid-state chemistry. In our first part, we looked at the structures of some common compounds, metals, and binary and ternary solids. In this section, we will learn about the radius ratio rules to help us predict what structure a compound might prefer, and then also we will learn about some defects in the lattices and non-stoichiometric solids. Later we'll learn about the bonding in solid compounds using ionic structures as well as band theory. So before we saw that a series of different types of lattices for simple ionic compounds, and the first thing to consider when trying to decide what structure might one predict for a compound would be to consider the stoichiometry. So we saw, there are AB type compounds, AB2 type compounds, and then ABX3 type compounds. So that narrows it down a little bit. Next, we consider the relative ionic radii, and in this case we're going to define the radius ratio as the radius of the cation divided by the radius of the anion. So this is why this is a factor, is that the size of the holes varies. So we've seen tetrahedral, octahedral, and cubic holes. So those have different sizes, so one could put a different size cation inside an anion lattice with those holes. So the anion lattice would determine the hole size, and then what cation would just fit inside that would be the critical radius ratio. We'll see that there are some challenges to applying the radius ratio rule, in that the ionic radii of the elements, there's a table in your chapter 2 of your textbook and another table in the appendix. You can't directly measure the size of the ion, and so one has to estimate the radius using some kind of theory or parameters, and so then depending on which radius you pick, which list you pick from, that might affect how effective this radius ratio then is going to be. And finally, we need to consider the covalent character of the bond in the compound. So all bonds are somewhere between ionic and covalent. So we'll call it polar covalent. And there's also not on here, but metallic bonding. And so really we should look at a bond type triangle to understand when we're to compare what we're actually looking at with the compound we're interested in. And one such bond type triangle is called the Keteler triangle. And so depending on electronegativity, that will tell you whether a bond between element A and element B, where it lies on this gradient between ionic, covalent, and metallic. And why this is important is that ionic bonding, we think of ions as hard spheres with charges, and so they attract each other in a non-directional way, in a spherical way. In the same way, metals share electrons between atoms touching and close packing, and so that's not really directional either. But covalent bonding is directional, as we've seen earlier in chapter 3 when we looked at bonding in molecules. We would predict, is it trigonal pyramidal or something like that. So if we have, considering how much covalent character is in a particular bond, it might just determine, well, this bonding direction is going to prefer a tetrahedral or octahedral geometry. Okay, so what exactly is the radius ratio rule? And to help us understand that, let's look at cesium chloride lattice. So again, this is a little picture showing you that we have a cube, we have the chlorides at the corners, and if we assume the chlorides are space filling so that they just touch, which I'm not showing in this drawing here, the closest they could get would be along this edge here, edge E, excuse me. The length of this edge would be, if this is the radius of the anion, if it's touching, then that would equal 2 of the radius of the anion. So then how big is the hole here? We actually need to look at the body diagonal in this cube. So I haven't quite drawn out the cube yet. Let's finish drawing the cube here. So the body diagonal, again, there's another anion here. Body diagonal through this cube is where the cation is going to go in the center here. So that distance B in a cube is equal to, if we do some geometry, square root 3 of the edge. Okay, and then again, if we assume everything's touching, we have radius of the anion, radius of the cation, radius of the cation, radius of the anion. So RA, RB, RB, RA. So the bidiagonal equals 2 RA plus 2R, C cation. And we know the edge is 2RA, so we can figure this out here, do some algebra, set these two things equal, and so do some algebra, put RC on one side here, divide through by 2, and so then the radius ratio, if we divide RC divided by RA, is going to be equal to the square root of 3 minus 1, which equals 0.732. So for the cesium chloride structure, if everything is touching, so we're contracted as much as we can be, we're following Spinoza's principle there, then the radius ratio would be 0.732. And that's this number right here. That's saying that we could have an 8 coordinate coordinate structure, or the cesium chloride type structure, if the ratio between the cation, again remember the radius ratio is defined as the radius of the cation divided by the radius of the anion, is greater than or equal to 0.732. We could always put a larger cation in there, and that would then spread out the chlorides. If we put a smaller cation in there, say something that would be appropriate for coordination number 6, then the anions are touching and the cation is not touching, and so there's a gap there, and that would be less stable. So that's why these are called the critical ratios. So above this ratio, coordination number 8 would be preferred. Below this ratio and above 0.414, we would get the rock salt type structure, coordination number 6, octahedral holes. Below 0.414 and above 0.225, so the smaller hole is the tetrahedral hole in such structures as the zinc blend. And I guess we should also mention that you could have a radius ratio of 1, which would be a larger hole, coordination number 12, which is actually the close packed structure you see in metals and alloys. The limits, again, of the radius ratio rules are that you need to pick the right radii, ionic radii, and these are just the critical ratios. You could always put a larger ion in and just spread everything out more. So with that caveat, let's see what happens here with the compound beryllium sulfide. So beryllium, its ionic radius, we're going to assume it's coordination number 6, because that's in the middle, so that's kind of like an average value, and the radius for that cation in the appendix table of your book, 45 picometers. And then sulfide, again assume coordination number 6, radius of that anion is 184 picometers, so the radius ratio is 45 divided by 184 equals 0.245. So 0.245 is greater than 0.225, so we would predict a coordination number of 4, actually, or a tetrahedral hole. And so then that gives us two choices of anion lattice. Could either be cubic close packed with beryllium in, it'd have to be half the tetrahedral holes because it's a 1-to-1 stoichiometry, AB stoichiometry. So that leaves us zinc blend or wurtzite. And we saw before these are actually polymorphs, and so the compound could easily exist in either structure, and the known structure for beryllium sulfide is zinc blend. So our radius ratio rule and our ionic radii gave us the correct answer. And this works, I'd say maybe 70-80% of the time. So it's a rule in the sense of a trend rather than a law. Okay, so those are simple ionic compounds, and in reality the structures are more complex because we're not at 0 Kelvin, and so defects can exist from the perfect lattices that we were looking at. So let's look at a couple examples of defects. In this rock salt type structure, we see that we're missing one of the chlorides that should be there, and then we're also missing one of the sodium ions that should be there. So they're both missing. The charge doesn't change at all. This is a vacancy, and called a Schottky defect. So, but the compound, the charges remain unchanged. Here we have maybe just a slice of that sodium chloride structure, and you see that this sodium ion isn't where it's supposed to be. It's been moved over out of position and is occupying a position more between these chlorides. This is called a Frankel defect, and another way to think about it is a self-interstitial, where an interstitial position is an opening in the lattice where there isn't an atom, and so one of the atoms in the compound is moved into one of these interstitial positions. So again, the stoichiometry doesn't change, the charge doesn't change. Well, what about the stoichiometry could change? For example, here we have something different where there's supposed to be a chloride, and maybe we've heated up the structure and it's lost chlorine and left the electron in this hole, and this is called an F-center defect because from the German Farbe, which is the word for color. So sodium chloride is a colorless compound. When you excite the compound, maybe heating it, or we can excite it with our X-rays, and it will lose chlorine, leave these electrons. Now these electrons are free to move around and will actually give color to the compound. So this losing of anions or cations, it could be done as well, or it could be done intentionally. You can intentionally mix different ions in there, and that would be an example of doping. And these defects are going to change the stoichiometry because now we don't have the 1-to-1 sodium to chloride ratio. And it's also going to change the conductivity, change the color, because now we have charges that can move around easier. And that's again why doping is done, to modify the properties of the material. And we'll learn more about doping when we talk about semiconductors. Another non-stoichiometry with a solid is intercalation, which is defined as the introduction, or I'd say addition, of an anion or cation, an ion, into interstitial sites. So we talked about interstitial sites before. And here we have the unit cell for the structure of zirconium hydrogen phosphate. And there's some waters here, I think. And these waters, you can see, are between these layers of the zirconium hydrogen phosphate. So they're easy to move, and so we could replace the water with a different guest ion or otherwise, and that would be intercalation. We could maybe just replace one of the waters or replace all the waters in the structure. So again, it would be non-stoichiometric, depending on how much the reaction proceeded. So thank you for your attention, and we will talk about the thermodynamics of solid bonding in our next lecture.